sign. Okay, we'll begin, and so today I thought we'd talk a little bit about neural networks. Okay, and we'll do like a very basic introduction and do kind of the most basic form of a neural network here. Okay, and I don't know, maybe you've heard of this before. Maybe you guys are familiar, maybe you're not. And so we'll take a look, and we'll start off with a very simple example, and then we'll work up to do a slightly more complicated example. But again, this is going to be the most introductory type of neural network that we can create, and then there's going to be lots more. Were you guys able to check out the videos that I sent out and watch those? Okay, the short ones at least. Okay, so I'll kind of walk through basically the same things that short series of videos talked about, and if you understand today's lecture and you go back and you rewatch them or watch the longer videos, I think it will give you a greater appreciation or a deeper understanding, so it's good. Okay, so with the Welch Labs series of videos, we looked at he had two inputs. Okay, so our inputs, which we will put in our X matrix, our inputs here were hours slept, we'll say hours of sleep, and hours of study. Those are our two inputs, and then the output, our Y, would be the test score. Okay, and in our very simple example, we have 3 test cases, which is probably not the best, but if we slept 3 hours, we studied 5 hours, got a score of 75. We studied 5 hours, slept 5 hours, studied 1 hour, got a score of 82, and 10 hours, 2 hours of study, a score of 93. Okay, and so the question is, so this would be considered our training data. So this is what we are going to use. We use this to, quote, train our network. And our test case will say, let's say this comes in, what is our output Y going to be? So this is our test case. Okay, and effectively, all this is it's just a function of 2 inputs that spits out 1 output. That's really all it is. Okay, so we have inputs. We have 2 of them. They go into our function, which we call a neural network. And then it spits out an output. 1 output, which in this case is our score Y. Okay, and the way this is going to work is we create little neurons or nodes. Okay, and so because we have 2 inputs, we've got X1, which will be our hours of sleep, and we have X2, which is our hours of study. We will have 2 nodes in what we call the input layer. Okay, so we'll have 2 nodes in the input layer, And then we create something called a hidden layer. And the hidden layer will have more nodes. Here we'll just arbitrarily choose to have 3 nodes in the hidden layer. And our inputs will go to each of these nodes in the hidden layer. Okay. And then from the hidden layer, we will go to the output layer, and the output layer will have 1 node because that's just the score. This will be the output score. Okay. And all we are effectively doing is we're going to take each of these values, like 3 and 5, those are the 2 values here, and we just multiply them by some numbers. We do a little bit of, we do some math here. We apply a function. Usually at each node we apply a function. It produces another value, and then it continues on, and then we combine them to something, and that's going to be our output score. Okay, it's yeah, we can just think of it as effectively it's a function of 2 inputs with a bunch of kind of parameters that say how can we combine these 2 inputs, or however many inputs we have, what can we combine and process to get an output that looks like what we want to get. Okay, you can definitely make your networks much more complicated. Okay, so depending on how many inputs you have, all right, so you could have many inputs, and you could have several hidden layers. Before you get to some output layer, all right? And then all of these, you'd have all sorts of, basically all of these things are connected, and then same with this. Every single one is connected. And if you have a bunch of layers, we might call this many layers, we might call this deep learning. But to keep things simple, we'll just have 1 hidden layer, and for our early examples, this is more than plenty. Yes, question.
Just to clarify, because I feel like I've read a lot of it buzzword right now. So just like the key distinction is deep learning has just more additional layers. And that's probably
Yeah. To a certain degree, yeah. When we're talking about deep learning, it's generally some kind of neural network that has multiple layers in it. Now, what happens at each layer can be more complicated than what we'll do today, but effectively, that's what it is. Yes, it is a buzzword, but pretty much, all of machine learning is a buzzword fest. I mean, it sounds like machine learning sounds a lot more interesting and suddenly appealing than it is to say finding a function of many variables, right? But effectively, that's what it is, right? It's if you say, oh, I'm helping the machines learn, that sounds really cool. It sounds much more cooler than saying I'm trying to find the correct set of parameters for a function of many values, right? But effectively, that's exactly what we are doing. Yeah. So, and deep learning sounds much better than multiple hidden layers, but but that's what it is, right? So, okay, so we have a little bit of kind of notational stuff. We'll often call our So we have the input layers will be X, okay, and then here, let me copy this. Let's see. To our next slide here. So yeah, so our input layer, this is going to be our matrix X. So keep in mind, so X, this is a matrix. And in our case, our matrix had is a 3x2 matrix, okay? It is, we have 3, 5, 5, 1, and 10, 2. It is a 3x2 matrix. In this case, the 3 is the number of training examples. And 2 is the number of kind of input variables. So in this case, we have 2 input variables and 3 training examples. Okay. Our hidden layer, we will call these values here is Z superscript 2, 2 indicating it's kind of at our second layer here. Okay. The way we're going to get Z2 is, what we're doing is we're going to take each value and we're going to basically spread them out, or not spread them out, but we're going to multiply them by different weights. So we see each of these arrows, each arrow represents a weight. Okay, so we have a weight here going from x1 to basically the first node in the hidden layer Z, and then we have a weight going to the second node in the hidden layer Z, and then we have a weight going to the third node in Z. Yes?
Is there a bias term?
Yes, there is a bias term. Not in this example, I'm going strictly from what Welch Labs does. We will, when we look at the handwriting recognition data set, we'll introduce a bias term. But yes, we'll do that as well. Okay. I mean, we could have this. So effectively, if we look at just this thing, we're going from x1 to Z1 in layer 2, and this is going to get multiplied by the weight from 1 to 1. So this is weight 1, 1. Okay, and then, sorry, let's, should use different colors here somehow. Okay, and then here I have x2. This is also going to the same node, and this will have weight 2, 1. Okay, so this is, when we look, and oh, I'm sorry, this has a superscript of 1 to say it's kind of in the first weight matrix. So this is, we're just looking at kind of this little subsection here, okay? And so if we look at what Z consists of, this first Z value is going to be the value x1 multiplied by our first weighted value plus x2 times our value there, okay? From node 2 to node 1, okay? And then, and so that's what we have here. And we could do this. So in our first set, we would look at 3, 5. It would be 3 times weight 1, 1 plus 5 times weight 2, 1. Okay. And so if we look at this, we're going to have a total of 6 values in our weight matrix. Okay, so W1 is a matrix with 6 values. It is a 2 by 3 matrix. Okay. The reason why it's a 2 by 3 matrix is that you have 2 nodes going into the weight matrix, and then after being multiplied by the weight matrix, you have 3 nodes, right? So we're going from X, we're going to multiply it by the weights. After we multiply it by the weights, we have 3 values. So 2 in the input layer, and then 3 nodes at the next layer. Does that kind of make sense? All right, and so in this case, if we have a 3 by 2 matrix, so if X, and we multiply it by weight matrix W, X is a 3 by 2, and weight matrix W is a 2 by 3, what's our output going to be? Our output will be a 3 by 3 matrix, okay? So we've got 3 by 2, and then 2 by 3, and we will get a 3 by 3. This time, the 3 rows, each row corresponds to what? 1 observation, and each column corresponds to 1 node. Okay, so go, right, so here I've got, 3, 5, 5, 1, 10, 2, and then over here I'm going to have weight 1, 1, weight 2, 1, weight 1, 2, weight 1, 3. And after I multiply this, I will have 3 times weight 1, 1 plus, yeah, it's not all going to fit, will it? Plus 5 times weight 2, 1. This is going to be for the, we'll have, wait, no, I'm sorry. After I multiply it by this, each column, I gotta do this, so we go across, across, across. Oh, each column will be for the observation, and each row will be for the node. I apologize. Okay, so 1 column for each observation, and 1 row for each node. Okay, so in this case, we happen to have 3 observations, and that's why it's going to be a 3 by 3 matrix. But where am I? Sorry. Okay. So that's what we have after going from kind of the first to the next. And so so here we have z here, and then what we will do is we're going to apply a function to z. So we multiply all of these values, and then we apply a function to z. So the idea here with applying the function to z is yeah, we're basically transforming all of these values. So so again, we have z at the second layer here is kind of x1 times the our first times our second. And then once we get this, we will apply a function to z, and this will we will call a, and this will be our a2. And then let's see if I can just move this along here. So we go x times our weights, weight 1, we get our second layer z. Coming out of z, we have our a, and then we multiply the a times another set of weights, and we get another set of values here, but in this case just 1. So we'll call this z3, okay? So so we have our a's, and we're going to have, basically, after applying the function, we have an a1, an a2, and an a3. And then we will multiply a1, a2, and a3 by a set of weights. So we'll do, a1 times in the second weight column, second weight matrix. There's only one output, so we've got a1 times that from the second node, and from the third node, and these all get combined to form our second value z here. Okay, so we've got basically just a single matrix. A column matrix here, and we're going to have a single value z, and then we will apply a function to this value z2, and this will be our output, which is our predicted y. Okay. So kind of the steps here, this is multiply input matrix X by weight matrix W1. Okay. And then apply a function. This is in the basic version where you apply a sigmoid or a logistic function. Apply a function to z to get a, and then multiply the outputs of that function. And then apply a function, multiply the outputs of that function by weight matrix 2. And then apply a function to the final output there. Okay, so yeah, once again, kind of in matrix notation, we'll start off with kind of our inputs x. We multiply it by our weight matrix 1 to get our z's. We will apply the function to z's to get our kind of our activations at the second layer. And then we'll multiply the activations, the output of applying the function, we call that the activations, to the second weight matrix. And then lastly, we'll apply a function here, and this will be our y hat. Okay, so x, yes?
What would the dimensions of W2 be?
W2 would be a 3 by 1, okay? So x is, x would be n by 2, so n observations times 2 inputs. W1 is 2 by 3. I think now that I see this, I think I labeled that thing wrong. It's 1 row per observation and 1 column per node. Yeah. So n observations, 2 nodes at the for input x, and then we have 2 nodes in and 3 nodes out. So the result will be z2, which will be n by 3 for n observations and 3 nodes. That's going to be our z. We apply the function to z. And it applies element-wise, so A2 is still going to be n by 3. And then A2, our activations here, is n by 3. And W2 is going to be 3 by 1 in our situation. So this is n observations and then 3 nodes at the hidden layer. And then W2 is 3 nodes going in, and we have 1 node out. So the result of multiplying this is going to be Z3, which is going to be n by 1. N observations and 1 output node. And then we apply the function to Z3, which is going to be n by 1, and we will have n by 1 predictions. So let me, is this okay? All the dimensions of each matrix being multiplied together? I know it's a lot. But yeah, again, the picture is we've got 2 at the input layer, and then we've got 3 in the hidden layer, and then 1 in the output layer. And you can kind of see how the lines represent how many weights you'll have in each matrix. And so here, going from the hidden to the output layer, we have 3 nodes at the hidden layer, 1 in the output layer, so we have 3 lines, and so our second weight matrix will only have 3 elements, and it's 3 by 1. Yes.
The fifth layer is driven by the number of features that.
Yes.
So the hidden layer, does this need to declare, or is that?
Yeah, the hidden layer, it's really it's kind of arbitrary right now how many nodes you want to select in your hidden layer. There's not a whole lot of reasoning behind it. It's very arbitrary. But yeah, so if you might have 600 features coming in. You'll have 600 nodes in your input layer, and then but maybe for whatever reason for your hidden layer you want 20 nodes in your hidden layer. It's totally fine. Okay, so the first weight matrix will have will be 600 by 20. You'll have the first is for how many nodes are coming in, and then the second will be how many nodes going out. So if you if you have 10 million observations, you got 10 million by 600, and then you multiply that by the 600 by 20 matrix, and now you'll have a 10 million by 20 matrix for the z's there. And you apply your function, and so on and so forth. So here we're going from n by 2, and we're going to, after we multiply it by stuff in between, we get an n by 1 output. Okay. So let me, I know I messed up that one slide a few things back. So one row for each observation and one column for each node. This one back here. Okay, so that that process of going from the input, multiplying by the weights, applying a function. So we'll have the kind of input matrix, times weights, maybe plus biases, and, add a function or apply a function, so on and so forth, etc., etc. This is known as forward propagation. Okay, and so yeah, if we wanted to add biases, you would just be adding a column vector, a column matrix of bias values to the results of multiplying by the weights. So I'll just do that really quickly. So if we have x, our input, times kind of our first weight matrix, all right? And this gives us our first kind of our set here. So this is going to be n by 2, and the weight matrix is 2 by 3, and so now we're at n by 3. And here what we would do is we would just add some biases here, and in this case, yeah, basically the biases is basically 1 by 3, but n times, duplicated n times. Okay, so you have kind of your 3 nodes at the next layer. And then we would add, after multiplying by the w's, we would basically just add a b1, a b2, and a b3 before plugging it into the function. Okay, and so here we just have the same 3 values, b1, b2, and b3. And then we would duplicate that n times So you have a total of n rows of B1, 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 B2, B2. And B3, 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 dot, 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 B3. Okay, so you have all of these just so that everything gets a bias applied to it. Okay, and then you would continue on, and you would just do the same at each point you have a z. And then you would apply the function to the result of this. Yes. Yeah. So the problem with neural networks is that they don't have much interpretability. Okay, there's not like you look at the resulting numbers that you find, and you can't draw insight from it. Neural networks are just good at like, we were able to come up with some system so that when we put in new values, we can get good predictions. You have no idea what biases to put in. Everything happens in this magical training step. It's not even magical, but there's a training part, like the weights to use, the biases to use. Even in the simplest network that we're creating here, we're going to see that there's a ton of parameters to adjust, and it's pretty crazy. And so we don't have like with regression, like linear regression, like we have nice interpretability of each of these resulting coefficients. Neural networks, you lose that. You're trading away interpretability for fairly good prediction performance. The biases are just generated through the system, and it just allows a little bit of additional set of flexibility in the training. So when we basically right now, if we just did x times w, we just take each x and we multiply it by a w, and we get some kind of basically some product here. The bias is just I want to shift that resulting value up or down. That's it. Okay, it's just we're just doing that. Okay. Yeah, each bias is different at each node. Yes. So here at our hidden layer, we have three biases, three different bias values, but those three bias values are applied the same for all n observations. So you can't have different bias values for different observations. All observations will get the same bias values, but each node will have a different bias value. But the nodes themselves don't have interpretability either. It's just we came up with this spaghetti system of we're going to take numbers, multiply by some numbers, and we're going to keep multiplying by numbers. And then, oh my gosh, somehow it predicted the right value. And it's a little bit silly in that way, but the predictive performance of this thing is really good. so we use it, but we don't have it's not like a linear regression or even a generalized additive model where you kind of understand how the inputs affect the outputs. Here it's just like I've got inputs, I've got mystery, I've got good outputs. It's modeled after like the way our brain works. We don't really know what happens in our brain. We just know we see things and we can think things. But how is it that just a billion neurons somehow is able to make conscious thought? We don't know. But yeah, with the biases, we just apply them and they go through.
Isn't there like a relationship between the weights and the inputs? You can see which inputs are weighted heavier than others.
Ideally, yes. Practically, no. So yeah, if you look at the weight matrix, it turned like you just can't really make too much sense of it. But but yeah, we'll here. Let me continue going on here. We can talk about all of these implications of this stuff. Okay, so the function that we apply, a common choice, or at least in these basic vanilla. Where am I here? Common choice for the function f is the sigmoid function, okay, which is pretty much like a logistic function, okay, and that's f of t is equal to 1 plus e to the negative t, or it's basically e to the t plus 1 over 1 plus e to the t. Okay, this is our sigmoid function, and basically this allows us to go from, it goes from 0 to 1, right? It maps from negative infinity to positive infinity, gets remapped to 0 to 1. Right? So you go from at 0, it's at 0.5, and then, you know, as we go to positive infinity or as we go to negative infinity in this direction, everything gets remapped to 0 to 1. And a lot of times, as far as the inputs go, we will scale our inputs to all be 0 to 1, and we scale all of our nodes and all of our inputs so they're on the scale of 0 to 1. Okay, that's just often how we do our matrices. So we will often scale all inputs between 0 and 1. Okay. All right, and so so we'll just stick to our basic one where we only have with no biases. Okay, so in our so we have a weight matrix 1, which is 2 by 3. So we have 6 nodes here, and then weight matrix 2, which is 3 by 1. So we have a total of 9 parameters to figure out. Okay, and so so we're going to just try to figure out what 9 values to use that will give us the best performance on our data. Okay, and so we create a loss function, and our loss function will often just be the sum of squares residuals, right? Squared residual function. So we have a total of 9 parameters to figure out. And so the way we're going to do this is to train our model. We will use a loss function to measure how good or bad our performance is. And so our performance measure will be kind of the sum of our residuals. So y minus y hat, we're going to square those residuals and add those up. Okay, so this is a squared residual function, right? And if we need to, like y hat itself can be expressed as just a big output of one big function, right, of our inputs. All right, so we'll use this, and okay, and so to find so what we want to do, so to find the quote best parameters, and not really even the best, it's just some decent parameters. What we want to do is to find the best parameters, we want to minimize the loss function. Okay, and we want to minimize the loss function by changing, the only thing we're allowed to change are changing the values in our weight matrices, okay? So we want to change the values in our weight matrices, W1 and W2, okay? And so to do this, we are going to use something called gradient descent, okay? Gradient descent. Okay, so what is, so maybe we need to take gradient descent. Okay, so generally, like, let's say you have a function of one variable, and it looks, where's my, okay. What we're doing is, I mean, for us, it's easy to see where the minimum here. But the idea is, you know, here I've got, this is to minimize a function of one variable. It's very easy to minimize, right? But if we have, we've got 9 variables to minimize, a function of 9 variables to minimize, it's a lot more complicated. And so the way gradient descent works is you just kind of pick an arbitrary point, like right here, and then you find the gradient. The gradient is basically the multi-dimensional generalization of what a derivative is. Okay, so you take the derivative of a univariate function is the slope at that point. Okay, the gradient of a multi-dimensional function is basically the slope at that point, but it's a slope now in a bunch of dimensions, right? So, if, you know, because we can imagine a surface plotted over 2-dimensional space, the gradient there would be basically the slope, but for the 2 dimensions, and so it would point in, you know, some combination of those things, right? And that gradient would point you in the direction of the steepest ascent. And so if you want to find the steepest descent, you just go in the opposite direction of the steepest ascent. Okay. So gradient descent, so with one function, we do this, and we go, oh, the slope is negative. Okay, so the slope is negative. So if we want to go down, so we take a step to the right, or basically the next x point is going to be so x at time n plus 1 is x at time n minus the slope of ddx of f of x at point n. Okay, so we're just minus, multiplied by some little thing. So we take here and we say, oh, the slope is negative at that point, so we're going to take a step to the right, and we will move to there. And then we calculate the slope there, and we go, oh, it's negative again. So we move over here, and we keep doing that, and it's still slightly negative, and so we take a smaller step, and we go that way, right? In the opposite direction, it's the same. If you have something that goes like this, and you start off over here, you say, oh, your slope is positive. Okay, so then you take a step to the left, right? And then, so this is your next location, and then it's still positive, and as you go further and further, the slopes get more and more shallow, and so the steps you take get smaller and smaller until you reach the minimum, okay? It's using gradient descent, you can find local minimums fairly easily. It's really hard to tell if you're at a global minimum, okay? So local minimum, not too bad. Okay, so the gradient of a function is just, it's not ddx, but it's just kind of the combination of a whole bunch of partials. And so, in this case, we will use the gradient of the loss function. So okay, so basically we need to figure out what is the derivative of the loss function with respect to our weights, W1 and W2, okay? So what is the gradient or derivative of the loss function with respect to the weight matrices W1 and W2. Okay, and so we want to we've got to find the gradient with respect to each of these things. So we want so we'll get the kind of the partial of our loss function with respect to our W1 matrix. Okay, this is, we want to get this. We'll also need to get the partial with respect to our second weight matrix. This is what we want, because effectively to improve our weights, we will take our current weights, take our current estimates, W at time n, and what we're going to do is we're going to subtract off basically a this is kind of a small fraction of the gradient of our function, okay, with respect to of the gradient. So in this case, our loss function at the what's the gradient at our current set of weights, okay, and this is going to be the next set of weights we use, okay. Once we've taken a small step, we recalculate the gradient, and we're going to take another step. So it's so at each step we're calculating which is the direction that points to the steepest climb, and we go in the opposite direction. We just take a tiny small step. Yes.
Is that your learning rate?
Is it called your learning rate? Yeah, I guess it's your learning rate.
Is it usually alpha?
Let me see. It could be alpha. I mean, here we're happen to be using lambda, but I suppose it could be another letter. Let me think. It's just so we don't take too big of a step.
Yeah.
Yeah. So, yeah, any arbitrary letter. I'm happy to be using alpha or something. Okay. But yeah, so what we want to do is we want to find basically what is the gradient at each of these points, and we'll just take a step in the opposite direction. We update all of our weights, and then and now that we have that, we recalculate the gradient. We take a step in the opposite direction of the gradient, because the gradient is which way does it increase the most, so we take a step in the opposite direction, and that will tell us how it decreases, and we just keep doing that. All right, is this so far, is this okay? All of this goodness here? Okay, just to keep in mind, because the weight matrix 1 is a 2 by 3 matrix, the gradient with respect to weight matrix 1 will also be a 2 by 3 matrix, because the gradient is basically how each of those things need to change in order to give us the steepest descent. Okay, so because there's 6 values to change, there needs to be 6 values in our gradient. And same thing with our second weight matrix. It's a 3 by 1, so the gradient with respect to the second weight matrix will be a 3 by 1 matrix. Because effectively, if this is our gradient, the next iteration of weight matrix 1 will be our current weight matrix 1, which is 2 by 3, plus basically the gradient. And so the dimensions need to match up there. So that's kind of just a quick check to make sure, when we do our math, we are getting things of the right size here. Okay, so let's do this. Okay, so once again, our loss function is the sum of y minus y hat, not to the 1/2, squared. Okay, and just to kind of make things a little bit easier, I'm going to put in just a 1/2 here for the loss function. We just add this here just so that when we take the derivative, we don't have to have a factor of 2. It'll just cancel out. Okay, so we just add this here. It doesn't actually, the minimum of L and the minimum of L times 1/2 is going to be the same, right? So we just, the location of the minimum. So we just add in, 1/2 to make calculations a little easier, but it's not necessary. All right, so what we will do is we will take the partial with respect to weight matrix 2. Okay, and so we'll worry about the sum later, but so this will be dw2 of, okay, so we'll find this part first. Okay. Okay, and then so just keep in mind, y is our data, and so y does not vary with respect to our weight matrix 2. Okay, so changes to, what's the derivative of y with respect to weight matrix 2? There's no derivative. It doesn't change. Okay, so we only have to worry about how y hat changes when we adjust W2. Okay, so when I do this, I will get 2 times 1/2 y minus y hat. And then we have to apply the chain rule, and we'll have a -1 times dy hat with respect to W2. Okay, so this just becomes negative y minus y hat dy hat with respect to dW2. Okay. If so, we'll recall that y hat is equal to when we applied f of z3. Okay, and so f of z was the sigmoid function, which is 1 plus e to the negative z, right? So this is the sigmoid. And if we do, if we have, what is this called? Quotient rule for derivatives. The derivative of the quotient is u prime v minus uv prime over v squared. Okay, so f prime of z, the derivative of this is going to become e to the negative z divided by 1 plus e to the negative z quantity squared. Okay, so so when we take the derivative of this, we're going to get dy hat with respect to z, and z3 with respect to w2, and this part, that is going to be how y hat changes with respect to z. That's what we get here. Okay, and so our next part is going to be y minus y hat times, I'm going to just plug in f prime of z, okay, which is this part multiplied by the derivative with respect to w2, how the value z apply there, and then if we ask, okay, how does z, what is the derivative of z with respect to w2? Okay, let me yeah, I'll need to go on to the next slide. Can I change slides here? Okay, so we left off at y minus y hat f prime of the z function times the, how does z change with respect to the weight matrix. Okay, just keep in mind that what we had going on, so we had the w's, and then this gets to our z here. Basically, z will change with respect to w is based on the activations of layer 2. So this just becomes y minus y hat f prime of z raised at the third layer times the activation outputs at the second layer. All right. We'll just check the dimensionality here. Y is going to be n by 1. Y minus y1 is n by 1. And if we think of what is f prime of z3, we also have n by 1, okay? And so the multiplication here has to be element-wise. So n by 1, and also, oops, yeah, actually all of these things, we need element-wise multiplication. And A itself, we have n by 3. All right. So we've got n by 1, and n by 3. And so here we can do element-wise multiplication, and this would just be, that's what we have here. We can kind of shift some of these values around and turn them into a kind of matrix notation. All right, so if we shift to matrices, and we take the A2, which is n by 3, and we transpose it. Now we have a 3 by n matrix, and then over here, if I take y minus y hat times f prime times z of 3, I have an n by 1, and then thus when I multiply these together, I will get a 3 by 1, which is what I want, because again, this is the gradient with respect to our second weight matrix. Okay, and so we'll so in the code, what we'll see is this part we will call delta 3. We'll call this delta 3 in the code, and this will just be transpose of the A2 matrix. So this is, oops. Okay, so this is with respect to the second weight matrix. Okay, I know it's a lot. So again, we'll define. Effectively, I'm just trying to find the derivative of the loss function with respect to each weight matrix that we are using. Okay, and then so that was the first one. Then we have to continue on this, right? So if we continue this on to say, you know, what is the gradient with respect to the first weight matrix? Okay, pretty much all of the rules that we applied here to get to this point with respect to the second weight matrix applies, and we would just kind of pick up where we left off. So now we want to find what is the derivative with respect to the first matrix. We have the same steps as finding the derivative with respect to the second weight matrix. Okay, and so now we have. So this is where we kind of left off on the previous slide. So this is delta 3 here, and now we have to multiply this by the partial of how does Z3 change with respect to weight matrix 1. We stopped here in the other part because we said, at the second weight matrix, this, what happens before this doesn't really matter to us. Now it does. Now we're looking at this. Okay. So this part is still just delta 3. Okay, we can just use this as the same as before, and then we will split up the how Z changes with respect to first the activations in the second layer, and then how the activations change with respect to the first way matrix. Okay, we're effectively just applying the chain rule when we're taking all these derivatives. Okay, so it's just a whole bunch of chain rules that we are doing. So we're just doing D3, and this whole thing, with the fancy terminology, this is known as back propagation. Okay, but kind of using the same logic as before. How does Z change with respect to A? It changes by the weight matrix, and then now how do the activations change with respect to the first weight matrix? Well, like before, the activations themselves. Oh, I'm sorry. Let me. Yeah. So we have this multiplied by this transpose, and then this kind of splits. We're going to change A with respect to Z, okay, because we apply a function there, and then we're going to chain rule and Z as it changes with respect to weight matrix 1. So the way A changes with respect to the Z is just going to be, so keep in mind that A2 is the output of F applied to Z, and so the derivative of A with respect to Z is just F prime of this. Okay, so we have delta 3, W2 transpose F prime of Z2 multiplied by dZ2 with respect to W1, and lastly, okay, how did we get Z2 from W1? Well, we multiplied our input data X by W1 to get our value Z2. So this effectively just becomes X. All right, so our last line here times X, okay? So we might have to do some, just a little bit of moving things around. Okay, and so we'll transpose our X, and so we'll have 2 by n. If we transpose our X, we'll have delta 3, which is n by 1 multiplied by W2 transpose, which is 1 by 3. So these combine to n by 3 multiplied by F prime of Z2. So this is n by 3. So here we will do element-wise multiplication. And then here we will do regular matrix multiplication. All right, so let's just kind of put all this together. So we have X transpose delta 3 W2 transpose F prime of Z2. So we have partial with respect to W1 being 2 by n. This combines to be n by 3 multiplied element-wise n by 3. And so all of this becomes a 2 by 3 matrix. Okay, which is what we want. Okay, all of this we have. Okay, so now we can code this up, and I think I've uploaded some of this to CCLE, and you can look up download artificial neural network on your machine if you want, and we'll take a look at the code here. Okay, so are you able to read that? Kind of. All right, so we'll just start off with our training data X. Okay, so if I look at X, there's our training data, and then our outputs are Y, and this is our training data. And what we're going to do is we're going to kind of put everything on a scale from 0 to 1. So we're going to just take each column and divide it by their column max. And we'll take Y and divide it by 100. Okay, so X, we basically took each value and divided by 10. And then we took the second column and we divided by 5. So now everything's on a scale from 0 to 1. And then and Y is also on a scale from 0 to 1 here. Okay, and we will, I'm going to use variable names in case at some point if we wanted to change like the hidden layer size, rather than having to search for everywhere where it says 3, we're just going to set hidden layer size to equal 3, and then we can change all of these things kind of later. So input layer size is 2, output layer size is 1, and our hidden layer size in this case is 3. Okay. W1 is our weight matrix. So here I'm just going to take the number 1 and have 2 rows, our input layer size, and 3 columns for our hidden layer size. So if we look at W_1, I have a 2 by 3 weight matrix here. And so here what we will do is we will do matrix multiplication. In R, that's %% for matrix multiplication. And we say X multiplied by W1 is going to be Z_2. Okay, so Z_2 is a 3 by 3 matrix. Okay, 1 row per observation and 1 column per node. I have a function called sigmoid. All this is it just applies the sigmoid function. It takes in our Z, and this will do it element-wise. So I create a function called sigmoid, and if I do sigmoid of Z_2, we can see the results of applying that. If we wanted to just kind of create a plot to see what the sigmoid function looks like, there you have it. Okay. And so we will apply the sigmoid function to that matrix Z2. And so now A2 is the result of this. Whoops. Okay, that's what we have. So far we have X multiplied by our weights W, which result in a 3 by 3 matrix, and now we've applied the function F to that matrix Z, and now we have a matrix A, which we've called A2. And then finally, we're going to go from the middle hidden layer with 3 to an output layer with 1 node. So we're going to multiply this A2 matrix with a 3 by 1 matrix. Okay, so my matrix W2 is just a column of 1s right now. And so if I multiply that by this, then we get Z3. And now we have 3 values for Z. These 3 values for Z are kind of our the inputs right before we apply the sigmoid function. We have 1 row for each observation in our training set. And I apply the sigmoid function here, and we get our y hats, y underscore hat. Okay, so right now these are our current predictions based on our untrained weights. Right now our weights in every single thing is a 1, okay, which is probably not the case here. Okay, so this is what we have. We have y underscore hat. Okay, and then we also have the cost function. The cost function is just the difference between our output y, our prediction y hat, and squared. We sum that up, we multiply that by 0.5. So right now we'll apply the cost function to our actual values of y. Our actual values of y are 0.75, 0.82, and 0.93. Our predicted values of y are very much wrong, and so our cost of this right now is 0.0153. Okay, it doesn't sound like that's terrible, but this is a bad current cost value right now. Okay, so that was the forward propagation part. Now we want to figure out the gradients of all of these things. We did all of the math, which was, you know, I realized it was a lot of derivatives and all of this. Okay. And so, you know, we went through all of this. We've said, okay, this is how we are going to calculate the derivative. Okay. The nice thing about this is that this derivative works for basically all neural networks with one hidden layer in there. Okay. All you have to do is just adjust the dimensions of each matrix, but this is correct, right? You can, if you have 100 features, now it's going to be 100 by n, and then, you know, if you have 7 nodes in your next layer, it's going to be, you know, n by 7 or whatever. Okay, but that part's okay. Okay, so we went through, and this is kind of what we said. So we said the derivative with respect to W2, gradient of the second weight matrix, we said is this, y minus y hat times dy hat over dz3 times dz3 with respect to dw2. Okay, and so here we'll create a function for sigmoid prime based on kind of the quotient rule. So this is e to the negative z divided by 1 plus e to the negative z squared, and we can just kind of they created this plot in the video, and so this is the blue is the sigmoid function, and then we can see the derivative of the sigmoid function in green, and that makes sense, right? Because it is always positive, and it's the slope is steepest right here at 0. Okay, so delta 3 is this. It's y minus y hat multiplied element-wise times sigmoid prime of z3, and the cost function with respect to our W2 matrix is the transpose of our A matrix multiplied by the result of delta 3. Okay, so I think we have that in our notes. If I pull this up. Okay, so this is what we have. We said the cost function with respect, a derivative of the cost function with respect to W2 is the transpose of A2 times our delta 3, which is y minus y hat times sigmoid prime, the f prime of our z3, okay, which is exactly what we have coded up here. Okay, so probably the hardest part is going, not the hardest part. The math can be hard, but then it's also difficult going from the math to the code. But if you look, if you compare the math that we did and the code that I'm writing, I'm kind of doing a direct translation. Okay, I'm saying, okay, we got y minus y hat times sigmoid prime of this. Okay, and then we're going to multiply that using matrix multiplication times the transpose of the A2 matrix. So I have this. We have this, and so this is our current gradient with respect to the W2 matrix. Okay, and then if I continue on to calculate the gradient with respect to the first weight matrix, I get this. Okay, and so here I have a 2×3 matrix for the gradient of the first weight matrix and a 3×1 matrix for the gradient with respect to the second weight matrix, which is exactly what I want. Okay, and we will update the weight matrices by subtracting the gradient multiplied by some kind of scalar. All right, and I was just kind of fiddling around, and I guess I chose scalar to be 5, and so I will update my weight matrices. So right now, this is my current weight matrix, all right? And if I multiply that by the scalar, the gradient times the scalar, and I subtract that from our current weight matrix, and I do this, then I get, oops, this is my adjusted weights at the next iteration. These are the weights I'm going to use at the next iteration. And so the old cost 1 was 0.0153, and then we recalculated what our weights should be, right? So we used the gradient and we took a step in the opposite direction. So we now have new values for weight matrix 1 and weight matrix 2. So now we will do forward propagation and calculate our new predictions based on these new weight matrices. So I'm going to say x times weight matrix 1 is z2. We apply the sigmoid function to get a2. We multiply those outputs times the second weight matrix to get z3. And our new predictions will be after applying the sigmoid function to z3. So our new y hats is this. This is our kind of our new predictions. And so let's calculate the cost of our new predictions. And when we compare those two costs, indeed, the second cost function is smaller than the first cost function. Okay, so that's an improvement. So that's a good thing. Okay, and we would just repeat this, and we would recalculate the gradients, and then take a step in the opposite direction, recalculate our the weights based on that, and then recalculate our new predictions, and continue moving on in that way. Okay. What we can do is we can also do something called numeric gradient checking. Okay, so in we did the calculus to do all of this to find the gradient, but what we can do is also we can estimate if our are the gradients that we got, are those reasonable, right? So maybe in calculus you learned that you take the derivative with respect to the function and you get the tangent line right here. Okay. Another way, if you were unable to take the derivative of some function, or if you just wanted to make sure that your derivative is pretty close, what you can do is you can kind of zoom in on this region right here, and you can just take one location and go to another location. So you have x, and then over here you have x plus delta, and then you take the difference in the functions, f of x plus delta and f of x, and then kind of your derivative is going to be approximately equal to f of x plus delta minus f of x divided by x plus delta minus x, which just becomes delta, right? And this is actually the definition of the derivative. It's as delta approaches 0 that we get the definition of the derivative. So we can kind of mess around with this and just say, oh, what if we changed the value of x just by a tiny bit, right? And then see if indeed the gradient changes. I mean, if the see how much the function changes when we do that, and if we compare how much the function changes divided by the size that we altered x, that would also give us an estimate of the gradient. Okay, and that's the idea behind numerical gradient checking. Is, you know, we're going to just start off with a weight matrix. We get our current cost here, which we have here, and then we're going to do a tiny. We're going to change our values just by a tiny bit. Okay, 10 times e to the negative 4. Right. This is what we're going to do. Okay, and so our numeric gradient holder, we're going to start off with just a bunch of zeros, and what we do is we're going to kind of start with all of our weight matrices, and here I'm going to alter just one of the weights by 10 to the negative 4. Okay, so I'm going to I'm going to do this one at a time for all 6 weights. Okay, we'll do this one at a time for all 6 weights, and we're going to just add 1 times e to the negative, 1 times 10 to the negative 4 to one of the weights. Based on that, we recalculate the new predictions, and then we're going to take how much did our cost function change divided by how much I altered it. Okay, so so I'll go ahead and do this, and when I do this, this is kind of the estimates of my gradient, and then I do this the same thing for the other thing, and then we went through and we calculated the gradients there. So these are the gradients using kind of our calculus function, calculated using the work there, and then we can see how much our gradients are when we adjusted the numbers just by a tiny bit. Okay, so these values were calculated by taking our current cost, changing one of the weights by 10 to the minus 4, and then seeing how much how much the cost changed. Okay, and then and these values over here were calculated using kind of our calculus, and when we compare the two values line up very closely, which is a good sign. Okay, and if we compare that with you know, the other gradient, these values also line up very closely. They're off by a tiny bit, which is expected, but they're very close. So that seems to indicate to us favorably that when we did our calculus, we did it correctly, right? Which is always a good idea, because sometimes you go through a bunch of calculus and then you might have made a mistake, and then if you don't do a little bit of checking, you know, you could end up getting in trouble here. All right, so so here what I'm going to do is I'm going to just do gradient descent. So if you want to do this, I have the code here as well. So I'm going to just start off with some random weights. Okay, so I've got W underscore 1, these are my random weights, and W underscore 2, these are the random weights I'm using for my weight matrix. We'll keep track of all the different costs that we have, and then, oh, I'm sorry, yeah, we'll take a, after we do this, we'll take a quick break, okay? And then we'll do this, and then, so all I'm doing, if you look at this code, is I'm doing forward propagation. After doing forward propagation, I calculate the current cost. Then I calculate the gradients. And then once I calculate the gradients, I just adjust my weights by taking a step in the opposite direction of the gradient. Once that's done, we repeat the process. We do forward propagation, then calculate the cost, calculate the gradients, take a step in the opposite direction, over and over and over again. Okay, so we just, boom, it runs, it's done. Okay, that was really quick. All right, these are the resulting weight matrices. Okay, we look at this, these weight matrices don't have any practical interpretation to us. That's just the nature of the neural networks. It's hard to really get any kind of interpretation. Let's take a look at our predictions. The predictions that it produces are 0.75, 0.82, 0.93, which is very close to the actual values of y. Okay, so this is what we have. We look at the cost function output is very small. And if we take a look at how the cost function has changed, we see that, you know, in the beginning we got rapid cost improvement, then it kind of steadied off, and then it somehow made a breakthrough somewhere, and then the cost function has dropped off, and then it, you know, at this point we're not getting much cost function improvement. Okay, and if I plot on a log scale, we kind of see it in, and on a logarithmic value, we're still making improvements, just very small. Okay, you can also R has a optimization function. So here was applying the gradient descent manually. You could write the thing in terms of an optimization function. It's a little bit trickier because the optimization function only allows one vector of values to be optimized. Okay, so we have 9 values that need to be optimized, but it's just in one vector. So inside the function, you have to say, I've got 9 values, 3 of them go into weight matrix 2, and the other 6 go into weight matrix 1. And then after you do that, so here we have our kind of our data that goes part of our cost function. I take the values, the first 6 go into weight matrix 1, the last 3 go into weight matrix 2. We apply forward propagation, and then the last thing, this is what it outputs, the return value. This is the value function, this is what optim is going to try to optimize, is that last value, which is the cost of this. And then, and so we can do this, and when we do this, it prints out the results. This is basically the 9 values after optimization, and so here we have this. We have W1, which is this weight matrix, and W2, which is this weight matrix. And then when we do all of this, we see our optimized values are very close to the actual values. Okay, and you know, depending on where you start, you can end up getting different results. So here it didn't find the optimized value is kind of terrible, whereas this optimized value is much better, right? 10 to the negative 15, whereas this is on the order of, you know, 10 to the minus 3. Okay, so depending on where you start with gradient descent, you might not get optimal results. So because gradient descent is basically just rolling a ball down a hill. And when it reaches a low point, it's going to get stuck. And so unless your terrain is super smooth with just one global minimum, you're never guaranteed to find a global minimum. It can easily get stuck in some terrible location. So that's what we have. Okay, sorry, I've been talking forever here. Let's take a 10-minute break. We'll come back at 8 o'clock, and then we'll apply this neural network stuff to the handwriting recognition data set.